Good morning, everybody. We're starting today, finally, proper statistical mechanics. After we finalized, after we finalized the applications of thermodynamics to phase transitions. And what is the main difference, from my point of view, at least, between thermodynamics and statistical mechanics? So, in thermodynamics, we were very general. We described the system in terms of very few parameters. We had absolutely no understanding about what are the microscopical constituents of the system and how do they interact between themselves. Despite all of this, what we managed to do was, not we, the founders of this field, we go back to Thomson, etc., it was quite amazing. We got very general behavior that each system should satisfy in order to be in equilibrium. Okay, relations that connect entropy, energy, specific heat, etc., etc. And this theory was very successful in describing, specifically in describing the behavior of gases. But there is no true understanding in this theory of why everything works. We have postulates. The postulates are thermodynamical laws. Specifically, we used the first and the second thermodynamic laws. The first is just conservation of energy, and the second was something about entropy. Statistical mechanics tries to follow a slightly different path. It tries to take into account the microscopical interactions, maybe not all of them, but the most crucial ones, and build on top of this a consistent theory that eventually would go and continue on a macroscopical scale towards the basis of thermodynamics. But there is a problem. We already mentioned this a couple of times. The main problem is there's too many constituents, right? So even if we take small amount of gas of air, there are Avogadro number of particles. And there are a huge number of interactions between all of those particles. And how exactly can we take everything into account? We basically can't. It's just too much. Despite all of this, statistical physics tries to come out with an answer. Basically, we do need to take into account some specific interactions, maybe not all of them. And there is always a game between what we actually take into account and what we neglect. But the starting point is always some sort of a model of the microscopical reality. We will talk about Einstein model for solids, and we will specifically talk about what are the atoms and how we model them. Our modeling might be very naive and might be very far from the reality, but as we will see, sometimes it's enough to take into account very small portions of the total number of interactions. So how exactly statistical mechanics proceeds? It takes into account the microscopical picture. It tries to work not by determining what are the deterministic equations or the quantum mechanical equations, but mainly use constraints and mainly use statistical outcomes for the behavior. Okay? So this is why it's called statistical mechanics. It does not show how all the different molecules are actually moving, but it tries and appreciate the statistical flow, the statistical properties of the system. All right. Now, instead of using the words positions and particles and where each particle located, we will try and define specific states of the system. Now, a state of a system, it's very precisely described in quantum mechanics, right? So we can write a Schrodinger equation, ddt of psi equals the Hamiltonian multiplied by psi. Hamiltonian here is an operator, psi is a wave function, this is h bar, and this is a derivative with respect to time. And we know that for this equation there are specific stationary solutions for the psi. The specific stationary solutions are described by the stationary Schrodinger equation, is basically h, the Hamiltonian, which applies to psi. The specific number, quantum number μ, gives us the energy of the state multiplied by the same function μ. Okay. And all of those eigenvectors basically are describing different states of the system. So the system can be in either in one of the states which is described by a specific eigenvector, or a superposition of different eigenvectors. I'm assuming that everyone here is familiar with the bracket notation for quantum mechanics, right? You have seen this description of Schrodinger equation? Yes, great. Don't worry, we don't use it too much. You have a specific class on quantum mechanics. Now, when I'm saying that the system in a specific state, I can take all the eigenvectors that describe my Hilbert space and say, well, the state is described by by a representation of different eigenvectors, which are different wave functions for my quantum mechanical problem. I can always do that. The description might be very, very cumbersome and very, very hard to actually achieve, but actually it's doable, or at least we know it exists, right? So there are specific definite states, and when I'm speaking about a state of the system, from the quantum mechanical perspective, I can always say, what is a state? A state is a specific combination of different eigenvectors of my system, given that I'm using quantum mechanics in order to represent the problem. What I'm doing when I don't have a quantum mechanical representation. Okay, so if I only have classical mechanics at my hand, so what actually can I do then? Well, I can describe a phase space. And I think that you're familiar with this description from the class of analytical mechanics. And this phase space, each point in this phase space is given by all the different positions of my particles. So R's are the positions till. So I have n particles. Each of them have a position R, okay? And I also have n impulses, which are P's. P1, P2, Pn. So a point in my phase space, for example, if I have only one particle, then I will have P and I will have R. Consider, for example, a one-dimensional system when R is just the position along the one specific coordinate. So a point in phase space is just a point on this two-dimensional, for the case of one single particle, in this two-dimensional space, which is given by the position of R and the specific value of P. What is a state? A state is a sum, not exactly defined, volume around, very small volume, around this point in a phase space. Okay. So you see that I can, or I'm trying to use the same language of quantum mechanics, but I actually can't, because here everything is very definite, because I have different numbers and I can use those specific numbers in order to describe what is the state. The state is when the different quantum numbers are A, B, C, D, E. Here I'm trying to use a continuous representation and a state which is well, in quantum mechanics is something very discrete. Here, well, I'm trying to use this discreteness, but I can't because I don't have discrete values at all, or discrete states at all, or discrete spectrum, or a very specific eigenvectors in my Hilbert space. But what I can do, I can take a specific point and draw a small region around this point and call this region, okay, state of the system. So just a reminder, for example, if I would use a pendulum, okay, a very simple pendulum, which is have a string and a mass and position theta, the phase space for a given energy, when my energy is constant, the phase space is basically some sort of an ellipse. Okay? So these green lines are all the possible configurations of my pendulum as time goes by. Okay? And it basically goes from one position to another in this phase space. When I'm trying to describe a specific state of my system, what should I do? I actually need to draw a very small region on this line, and the size of this region would be my specific state space. Everyone understands why the phase space of a pendulum is just some sort of a ellipse, right? I hope you've seen it. Basically, what I need to write is an equation for the energy. The energy is constant, so the p squared plus theta squared, which gives us, so this is gives us the total energy. And this is why there is an ellipse connection between p and theta. And we also know that we can change the parameters, and this phase space can be transformed into something like this, etc., etc., etc. But for our purposes, we can plot all the different positions that are allowed by the mechanics for the system. We can draw all the lines in our phase space, and then afterwards, in order to choose a specific state, we go for a specific point, we just draw some small volume around this point. We will come to this point later when we will talk about canonical and grand canonical ensembles, but for our purposes, just now we do understand what is the state of a quantum mechanical system and what is the state for a classical system. While for classical system, it's a little bit ill-defined. How the system is going from one state to another. Here is the Schrodinger equation, right? We are in a specific we are in some sort of a superposition of states, and then we change the state according to the Schrodinger equation. What happened for the classical mechanics? In the classical case, well, we have the Newton equation, right? We just need to write F equals ma, okay, for all different particles. And this is how basically the system will change from one state to another. In our example over here, if we are at this point when we have a specific theta and specific p, okay, after a while the theta will grow larger, okay, I will go further and further away from the stable position. My impulse, my velocity will go smaller. Accordingly, my impulse will go smaller, and at some point I will stop. This is exactly this point. Okay? And then I will swing backwards towards the theta equals 0. Okay, so this is the dynamics. In the classical description, I'm following those equations, which are basically described by flow lines on my phase space diagram. All right, so we know how the dynamics works, how states are changing as a function of time. What we don't really know is how it helps us in order to describe statistically the system. I was trying to convince you that part of the statistical physics is to use some sort of a statistical laws, right? how the statistics is actually coming inside this description. Now, this is a little bit a point that one has to think about the system in perspective of phase space or eigenstate or state space, and think that the whole system is described as a point in this general state. Okay, so let's consider that I have a lot of states for my system. Okay, and I specifically describe all different states are as some sort of a rectangles that I draw on the whiteboard over here. So when I'm saying that the system is going from one state to another, what I should imagine, well, here I'm imagining that, well, actually the pendulum is just swinging backwards and forward. While in general I should think, well, I've been in this state, afterwards I've moved to another state, afterwards I might jump to third space, and I continued on and on and on. Okay. So in classical physics, I'm just going along this flow line in my phase space. In reality, in what I'm trying to convince you to think now, that when I'm telling you the system changes from one state to another, to the third, to the etc., just imagining that you have different states, and the system is basically performing some sort of a jump process from one state to another. In quantum physics, it's a little bit, it's hard to imagine how the system is changing from one state to another state as a function of time, especially if we are talking about that the system is sitting in its eigenstate, right? We know from quantum mechanics that if the system is in a specific eigenstate, it won't change its state forever until we do actually something. Okay? So this picture for quantum mechanics might be wrong, especially if we have a constant energy. Now what I'm trying to convince that, well, there's a lot of particles, and the quantum mechanical spectrum is very, very dense, so we don't really know at which system, at which energy the system is currently is. We never know it, and it never sits in its eigenstate. And if it sits in its eigenstate, there are always some small fluctuations, small interactions, even with vacuum. Okay? And those interactions would eventually cause the system to change its current state and jump to another state. Eventually, when we're looking on the system, any macroscopical system, what we see, it's constantly changing its states from one state to another, to the third, to the fourth, etc., etc., etc. And if we're trying to measure different states, and if we are trying to measure different observables, like for example energy, we can define average energy as something that we learn from a macroscopical observation of the system. Okay? We don't really know what happens on the microscopical level. We know that there is a lot of interactions and there are quantum physics involved or classical physics involved. Something happens, but eventually when we look on the system in our lab, we see that the system is changing from one state to another. For example, we are measuring its energy. So the average energy would be after we performed sufficient number of measurements, right? So the average energy would be 1 over n. N is the number of measurements. Okay. And here we just sum all the different values of the energy that we obtained. E of alpha. Okay. So we performed n measurements. For each measurement, we wrote down what is the energy that we recorded. We sum all of those energy together. We divide this by the total number of measurements that we have performed, and we obtain the average energy. Great, so we are now going towards the statistical description, somehow. All right, now let's rewrite this average energy and use, instead of, well, different measured quantities, values of the energy, all the possible values of the energy. So we can write the sum as the sum of the total of the all possible states of the system. So the sum is for the all possible states of the system. Okay. And here we have multiplied 1 over n. N is the same n as here. Here we would write the number of times state nu was visited, multiplied by the value of the energy at this specific state nu. Okay, so here it's very simple. We collect all the measurement data, we divide it by the total number of measurements. It's great. Here what we collect, well, we collect all the different values, of the states of the system, and we write down how many times we measured each of those values. Okay. After we have done this, well, we can say, but maybe we can write down this quantity, this average value of the energy a little bit differently. So we'll still use this notation. We will sum up over all the different states of the system. We'll multiply it by all the different values of the energy of the system. But this guy we will write a little bit differently. So we will write the average of the energy. It's equal all the possible sums, all the possible values of the energy, multiplied by the probability of the system to be in this specific state, multiplied by the value of the energy at this specific state. Okay. So what we see now, that we connect a macroscopical observation and microscopical calculation, because this is a static quantity. This is a probability of a state to be, of the system to be in a specific state, okay, being u. And more specifically, in order for this guy, E, to be equals to this guy, okay, what would have to be equal is that P mu should be 1 over n, the number of times the system visited state nu. This is not exactly a definition. This is something that I measure when I watch the system. This P nu is something that I compute based on all the quantum mechanical or classical mechanical description of the system. Right? I defined already the state, so I can compute the different probabilities. A general assumption in statistical physics that this equality holds, and when it holds, I'm saying that ergodicity is satisfied. So specifically this statement, that P nu equals the number of times the system visited state nu divided by the total number of measurement, is called ergodicity assumption. What we actually assuming? We're assuming that the system, as time goes by, actually visiting all the possible states of the system. It's not sitting in one specific state. It's actually following some very complicated trajectory, but this trajectory goes from one state to another, to the third, to the fourth, etc., etc., etc. And if I follow it for sufficient number of sufficient time, eventually it will go close by or through all the possible states that are associated with the constraint, with the system, that are allowed for my system to be in. Okay? And if I measure for sufficient time, the number of times that I visited each different state, I will see that eventually this quantity would converge to a specific value that I maybe, not maybe, but for sure, can compute from theoretical perspective. So this is temporal averaging. This is ensemble averaging. Why ensemble? Well, some sort of a statistical averaging based on specific calculations through the interaction picture. What I mean is that the system is mixing in a sense. It's if I have a phase space or all different states and I'm starting from a specific state, my trajectory will run through all the possible states and eventually fill up all the volume of my phase space, all the volume of my different states. Okay. This is an ergodicity assumption, and it's very important because what we are assuming that all the different macroscopical values that we can measure and afterwards can connect to some thermodynamical representations are also can be computed by the means of P and U, by the theoretical considerations, based on very specific microscopical picture. I'm sorry. So, okay, so what next? Here we have a route to compute different averages. How actually we compute P and U? We need some prescription. We need some sort of a way in order to compute all the different values of P and U for a given system. Okay. Here comes a specific drawback. And this drawback says, well, you need to assume something about the system before you rush in and say what are the different probabilities P and U, right? And this something that you must assume is called ensemble representation. What is an ensemble representation? When I'm telling you that, I'm assuming that this is a specific ensemble. I'm assuming a set of constraints that this system must satisfy. So for example, microcanonical ensemble. It's an assumption that the energy is constant. The volume is constant. The number of particles is also constant. So everything is constant. The energy is constant. The volume is constant, the number of particles is constant. Well, what might be non-constant? So there is a relation between energy, entropy, so we maybe might change the entropy a little bit. But we need to play with these assumptions right now for microcanonical ensemble. So maybe next week we will learn canonical ensemble and grand canonical ensembles. Canonical ensemble, energy is not constant. Temperature should be constant over there. Ground canonical ensemble, energy is not constant. The number of particles is not constant. Okay? We always try to do something or to actually change the different constraints, take some constraints in, take some constraints out, and eventually we can play around, but each set of constraints defines the ensemble. Ensemble defines the system behavior. When we say we are using microcanonical ensemble, those are the set of assumptions that we have made. Now, in quantum mechanics, or in statistical physics, or in classical physics, if I'm saying, well, my energy is constant, can I say something about the different probabilities of the different states? I actually might, because remember what we learned in thermodynamics. Okay? So in thermodynamics we learned that in equilibrium the energy is at minima. Okay? So we would find the system and in its minimal energy or its smallest energy in equilibrium. There might be some, we talked about fluctuations to different states, but eventually the system would like to sit, prefers to sit, according to our second law of thermodynamics, in its minimal energy, in an energy that its value is minimal. But if all the different states have exactly the same energy, right? We might say, well, they're all in a minima. What we are assuming from the microcanonical ensemble that if the energy is constant, all the energies are at minima, so all the states have exactly the same probability. So microcanonical ensemble B mu is uniform. So it doesn't matter at which state I sit, the probability to be at this exactly state is equal. It does not depend on the value of mu for this state. So if I have a concrete number of states, okay, if I have a concrete number of states, I know, so if what should I use it? So P mu is 1 over number of states. Right? This is my probability. The probability to be at each specific state is equal to any other state. They all equal, so it's uniform. And in order to satisfy their normalization, it's just 1 over the total number of states. Okay, so this is the microcanonical assumption. We know how to compute probabilities for different states. Okay, so this is great. We accomplished something. We maybe know now how to connect the dots and how to connect the different properties. Okay, but we need maybe another representation of a macroscopic quantity. So in thermodynamics, we had energy. Energy is constant. We cannot really play with it. We had entropy. We had all the different auxiliary functions like Helmholtz free energy and Gibbs energy and enthalpy, etc., etc. So we need a function of state. Although we start with a microscopical description and we can associate for each microscopical state the probability for the system to be in this state, okay, we still need something that relates to our macroscopical understanding on the subject. And this quantity, you're going to use what? We are going to use entropy. Why entropy? Now, because it's very meaningful to use entropy as we defined it as we already defined it and we know its properties from our thermodynamical perspective, and connect it to the different number of states that are allowed to the system. Because if you think about this for a second, so there is a very interesting fact about entropy. This is the variational principle, right? The energy is at its maxima with respect to applications of constraints to the system. So if I have a system, right? A general system, doesn't really matter. I have a box with a gas, okay? And I put a constraint, an internal constraint in the system, right? For example, I introduce some sort of a wall. The variational principle, which is an outcome of the second law of thermodynamics, tells me the moment I introduce this wall inside a system, the entropy goes down. Okay? Right? So this is we know. But think about what happened to the system in terms of the different states that are allowed now to the system. So there are a lot of gas molecules inside this. Okay? So I have this system without a constraint, and I have the same system but with a constraint. What have actually changed? So we know the entropy must go down, but we don't really know what's entropy on the microscopic level. But what we know is the moment we introduce this constraint, the particles are also constrained right now. There is no situation that a particle is actually sitting here. Why? Because there is a wall now. So it cannot sit on the wall. And also it cannot cross the wall, it has to go around. So the number of different microscopical states of the system is lower for a system with a constraint, and it's higher for the system without constraint. So in terms of the number of states, allowed states of the system, what we know is that the system without constraints, the number of states that are allowed for the system is always bigger for any system when we introduce some sort of constraint. It's pretty trivial, right? Because nothing cannot satisfy, and now all the states are allowed that satisfy something. So the number of states always getting smaller when we introduce a constraint. But we know that the entropy is also getting smaller as we introduce a constraint. So maybe, not maybe, but actually what it has to be done, we must associate somehow entropy and number of states of a system. Okay? So we know that they behave the same in terms of a constraint. The number of states is at a maximum when no constraints are introduced. The same goes for entropy. But there is a problem with this association. Why? Because, well, the entropy grows linearly with the size of the system. It's an extensive value. It's an extensive value, right? Extensive quantity. What happens to the number of the states? Is it extensive? Is it linear? So think about the following example. My system is a dice. Okay, I have a cube with numbers on it. So 1, 2, 3, 4, 5, 6. So the system, or different states of the system, each time I throw the dice, right? One cube, for example, and I have 6 different outputs. Each output is a state of my system. Okay, the chance to get 1 is equal to the chance to get 2 or 3. It doesn't really matter. I only have 6 states to the system. Okay, I double the size of my system, or the number, or by taking now into account 2 dice. Okay, so instead, each time throwing 1 cube, I'm throwing 2 cubes, and I'm looking on the different number of states now. What happens? So I have state which is 1, 1, I have states which is 1, 2. I have states which is 1, 3, etc., etc. So for each outcome of the left dice, I have 6 different states for the right dice. So for both of them, I have, instead of 6 states, 36 states. So what happens when I increase the number of, or the volume of the system? The number of the states grow multiplicatively. Okay, so it's, if I have 2 systems and now I connect them with each other, and assuming there are no interactions, as I'm always assuming, so the different, for each state of system A, there are n states of system B. And in total, when I connect 2 systems, the total number grows, is just a multiplication of the number of states for A multiplied by the number of states for B. Entropy is describing what? The number of states. It's describing something which is connected to A plus something which is connected to B. So it's not multiplicative. It's linear. So what should we do? So if omega is the number of states, we described S as K Boltzmann, and I would write, this is just a constant, of a logarithm, not a logarithm, of omega. Okay? So I have this association for the number of states from one perspective, but it also stays in an extensive quantity, because if I have 2 systems, the number of states is omega 1 multiplied by omega 2, but the logarithm of omega 1 multiplied by omega 2 is just the sum of logarithms. So this is my entropy. This is how I define it right now. What is K Boltzmann? It's a Boltzmann constant. And it has a specific value. This value is 1.38 multiplied by 10 to the minus 23. So K Boltzmann, 1.38 multiplied by 10 to the minus 23 joule per Kelvin. And why it's there? Well, it's there because 1 over T is equals to del S to del E, and this temperature has to satisfy the Kelvin scale. Okay. But this is just a constant for us. So now we have a very specific definition of a macroscopic quantity or a functional state that we used previously, the entropy, in terms of what? In terms of different states of the system. Number of states of the system. And specifically for a microcanonical ensemble, we also know how to compute the probability to be in each state. Right? So now the stage is set for what? The stage is set for actually trying and computing entropy, and afterwards specific heat, or all different other quantities for macroscopical or microscopical system. Okay? Everything that we need to know is already here, because, well, we need to assume something, and this is the microcanonical ensemble. We know what are the probabilities. We know how to write the entropy. Now we are capable of writing everything else, including all the different state functions. We can write specific heat. We can write different, how the system changes if we apply such force or different force. We can actually compute everything. What we need a model. What do I mean? A model that there we should compute the number of states using this definition of what is the probability for a state. So in thermodynamics at this point, I would say something very general and not exactly precise about a system. In statistical physics instead, I'm saying now is the time for something very specific and very precise. Now I have to go to a model, and now I have to go to a specific system and use this definition of entropy and this definition of microcanonical ensemble and its assumptions about how the different probabilities for different energy, for different states work, and then use it on this specific example. So this is the difference between thermodynamics, statistical physics, and statistical mechanics. We have to use very specific models, but they must not be too complicated. Otherwise, we will not be able to solve them. So what we are going to do now, to the end of this lecture and next hour, is we're actually going to use and show how the microcanonical ensemble and its assumption works for different systems. Now, the first system is a model of a solid. Okay, so we nowadays all know what a solid is. It's, well, at least a crystal, for example, is different microscopical atoms that sit in different positions. They vibrate a little bit, but they do not move, or they move together. And the microscopical picture would be of a lattice, and on this lattice we have atoms, right? Around each atom there is electrons. We don't really care about them, but this is a general structure. Okay? So think in two dimensions. Each point is an atom, and we know that atoms are interacting somehow with each other. They vibrate, they move a little bit, etc., etc. But we all know this because somebody told us. Now, go back more than 100 years ago and try to understand what's actually going on there, even before I understand that there are atoms and I'm not actually sure about the atomic structure. Okay? But I want actually to use my imagination in order to describe the system. I know it's solid. I know it doesn't, but it vibrates a little bit because it might have some elastic properties. And I want to describe it. Now, what I can measure, I cannot go, well, it's only the time of X-rays, etc., etc., but I want to actually somehow to connect my microscopical perspective of what's going on inside and macroscopical measurement of specific heat or elastic properties. This is the path of statistical physics, statistical mechanics. Let's start from a very specific microscopical descriptions and go to the definition what entropy is, okay, or what the temperature is, and what is the specific heat is. Specific heat we can measure. And then we can, if we measure something and it fits right to our predictions for a microscopical model, we'll say yes, this is what actually goes on inside. So this model of a solid called Einstein, of course, Einstein model, and it goes back to 1907, so 110 years backwards. Einstein assumptions were as follows. Very, very simplistic. The assumptions of Einstein as I have n atoms inside, or n particles. Each particle have 3 different degrees of motion. So it can vibrate or move in this direction. It can move in the perpendicular direction, and can also move in the z direction. So outwards or inside the board. Okay. All the different particles, the atoms, do not interact with each other whatsoever. Okay? They do not see each other. Their motions are not correlated with each other. They don't care about each other. What they care about? They care about their mean positions. So there are a very specific point that each atom is associated with this point. We don't really know how this point is defined, but it's very, very definitive. This is the lattice, and all the different points of the lattice, the particles are sitting and they're vibrating around this point. How they vibrate around each point, how each atom is actually moving, just like a harmonic oscillator. Okay? So think of it as the atom is actually a mass that is connected by a spring to a constant point, and it can do this, this, and this. And all the mass springs constants are constant and are the same for all different atoms, okay, and for all different directions. So for each degree of motion, I can write in Hamiltonian, okay, which is simply P operator divided by 2m plus 1 by 2m omega 0 squared x squared. This is my Hamiltonian, quantodynamical Newtonian. Don't worry, I'm not going to solve it. You have a class for it. But what I know that I plug it into a Schrodinger equation, and eventually I obtain solutions for the wave functions and the energies. Okay. So the wave function goes Fn 1 over square root of 2 to the power n factorial m omega 0 divided by pi h bar to the fourth power e to the power minus m w0 x squared by 2h hat, and the Hermite polynomials of a square root m omega 0 by h bar x. Okay. So this is the wave function that is associated with a specific quantum number n, which is the energy level or a specific state of each harmonic oscillator in each degree of motion. Okay, and different energy levels that are allowed to this harmonic oscillator are 1/2 h bar omega 0 plus n h bar omega 0, and I remind you that h bar is h divided by 2 pi. H is a Planck constant, and it equals to 1.05 multiplied by 10 to the power of minus 44 joule multiplied by second. So this is the solution for each degree of motion. How many oscillators do I have? I have n particles, n hat particles. So in total I have 3n number of oscillators. Each of these oscillators have a specific quantum number n that gives me its wave function and it gives me its energy. And I don't have any connections between all the different oscillator except what? Except that I assume, because I'm working in microcanonical ensemble, I assume that the energy of the system is constant. This is my constraint. The system is a system of non-interacting particles whatsoever. They don't care about each other. What do they care about? That the total energy, let's call it U, the total energy of the system is constant. U is constant. Total energy. Now, it looks like oversimplifying, and indeed, we'll see later that it's this system, this model it will fail us for specific quantities like specific heat. But this is a model. This is how Einstein maybe tried to understand what's happening inside the system 100 years ago, before we knew everything about quantum dynamics, we knew everything about the macroscopical structure. This is an assumption. But this is an assumption that we can work with, right? Because we can count states because we can look on the states of each different oscillator. Okay, we know we can predict what are the different energies, right? We don't care about this guy because we are going to work with probabilities, and we don't care about the exact wave function. We only care about the number of states and different number of states. Okay, and we know that we have a constraint that the total energy is constant. Okay, so this is our starting point. Well, maybe let me restrict a little bit. So in the Einstein model, while he was assuming that they are just simple oscillators, we can forget about this guy. Why? Because, well, the energy is indeed 1/2 h bar omega 0 plus n multiplied by h bar omega 0. So what this term is only doing for us, it's actually saying, well, what is the zero level of the energy, okay? And we can always shift it upwards and downwards. So the original assumptions are that each oscillator can have an energy of E of n is equals n h bar omega 0. So each oscillator can have an integer number of h bar omega 0, right? So the first oscillator can have 2h bar omega 0, the third oscillator can have 3h bar omega 0, fourth oscillator can have 0h bar omega 0, so we can go to the first, the second, the third, the fourth. I just number the two different oscillators over here, and this guy will have, for example, 2h bar omega 0. This guy will have an energy of 3h bar omega 0. This guy will have a zero energy, which is basically half h bar omega 0. Okay, so it's just 0 multiplied by h bar omega 0. Fourth will have, for example, 5h bar omega 0. What we know is that, we can continue, the total energy is what? Is integer, because if we sum all the different energies of all the oscillators, it's an integer number because it's composed from a sum of integer numbers as integer multiplied by h bar omega 0.
Why is the 3 0?
Because I chose it. I don't really know what is it. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So consider this configuration. It's purely random. Okay? All I'm saying that 3 can have 0 h bar omega 0, or 1, or 2, or 3, or 4. Now I looked on the system and I found this in this state. What I'm calling a state, the state is the first had 2, the second had 3, the third had 0, the fourth had 5. I can close my eyes, open them, and I will see, well, now I have 6, 7, 5, and 0 here. It doesn't really matter. It doesn't matter. Each state has the same probability. We know this from our assumption about microcanonical ensemble. So each state is exactly the same in terms of probabilities. What does matter? The only thing that matters is that I have the total energy is some integer multiplied by h bar omega 0. And I know that this total energy, U, is constant. So what is constant? U is constant. So U h bar omega 0 is constant, and it equals integer number. Okay? Because this is how I constructed my model. U is the total energy, is basically some integer multiplied by h bar omega 0. So U divided by h bar omega 0 is an integer number. The system will jump from one state to another, to the third, to the fourth. At each state, each of this oscillator is rotating or it's vibrating somehow differently. Okay, because it will have a different energy. All the different states are uni-equal. They are equal. The possibilities, the probabilities of all the different states are equal. But there is a correction or connection between everything. How come? I haven't assumed anything. How come there is a connection between how this guy vibrates and this guy vibrates? Because I'm assuming that the total energy is constant. Okay? So all different states always must satisfy that this number, u divided by h bar omega 0, is a constant number. I cannot see a state, okay, that the total sum of all the different energies, or the total number that stands here for each oscillator, will be higher than u divided by h bar omega 0. Okay? So this describes me what are the different states in my system. Now, the next question is omega. The total number of states. That are allowed for this system. How I write down omega? Big omega here. This becomes a combinatorial question, right? So what I need to perform? I have a lot of oscillators. Actually, I have 3n oscillators. Okay? This is an integer number. I also have oscillators. I also have u divided by h bar omega 0 quantas of energies. What I need to perform, I need to take all this quantas of energy. So here is an integer number. It can be 1, 2, 3, 4, 5, 6, 7. I don't really know how. And somehow to actually, not to relocate, but push some of these quantas to the first oscillator, some of these quantas to the second, some of these quantas to the third, etc., etc. So I have to reshuffle them, or shuffle them somehow, so a specific number goes here, a specific numbers go there, okay? But that the total number of oscillator is constant, and the number of quantas of energy is constant. So if we think that the quantas of energies are just apples, okay? So I have u divided by h bar omega 0 apples. And the oscillators are different boxes. So what I need to do, I need to put u divided by h bar omega 0 apples into 3n bar boxes. Okay, so what is my question here? So let's think that I have 1, 2, 3, 4, 5 apples. And I have 3 boxes. How I solve the problem? So what are the number of states is the number of ways to put 6 apples into 3 boxes. How do I solve it? Well, instead of trying to solve it using boxes, I'm saying, well, I have a separatrix over here and a separatrix over there. And I need only 2 separatrices. So this is the first box, this is the second box, this is the third box. Okay? So the number of ways to put 6 apples inside 3 boxes is the number of ways that I can plot 6 apples and 2 separatrix in different ways. The number of different ways that I can plot this picture over here, okay, is the number of the ways to put those apples inside the 3 boxes. Okay? And in general, for this problem, it is the total number of states is 1, 2, 3, 4, 5, 6, 7, 8. Okay? So it's 8 factorial divided by the number of reshuffles that I can perform between different apples, because this is one state, and if I will switch two apples, it's still the same state. Okay, if I switch those two apples, it doesn't matter. So it's divided by 6 factorial, and it also doesn't matter if I will start to switch those separatresses. Okay, those lines over there, I can switch them. It also doesn't matter. So it's 2 factorial. This is the number of ways in order to put 6 apples inside 3 boxes. Now what I need to perform, I need to put U divided by h bar omega apples, or quantas of energy, inside 3n boxes or 3n oscillators. I just generalizing this result. I just need to plot U divided by h bar omega 0 apples, and I have to put there 3n bar minus 1 sticks, and I have to calculate all the reshuffling, distinct reshufflings. In general, the number of states, omega, is just the number of objects that I have. What is the object? Quantities of energy and number of boxes. So I have U divided by h bar omega 0 plus 3n minus 1. Like here, I needed 3 boxes, I used 2 sticks. I need 3n boxes, I will use 3n minus 1 sticks. Factorial divided by 3n minus 1 factorial multiplied by U divided by h bar omega 0 factorial. This is the number of states that are allowed for this system for the Einstein model. There are n atoms, 3n degrees of motion, degree of freedom. The total energy is U. This is all the different number of states that are allowed for this system. I can go forward and say, well, if I know this, I know what's this entropy of the system. It's already an easy peasy problem, right? We know what is the definition of the entropy. Entropy, S, is KB ln of this guy over here. U divided by h bar omega 0 plus 3n minus 1 factorial divided by 3n minus 1 factorial. And here I will have U divided by h bar omega 0 factorial. Okay. I can continue this a little bit, and I will write down that S is K Boltzmann ln of U divided by h bar omega 0 plus 3n minus 1 factorial minus K Boltzmann ln of 3n bar minus 1 factorial minus K Boltzmann ln of what I left with, U divided by h bar omega 0 factorial. Right? This is an ugly formula because it has logarithms and factorials, but it's actually not that bad. Why it's not that bad? If U is big and n bar is big, so I have a logarithm of a factorial, can I do something with this? Stirring approximation. Have you heard about stirring approximation? Yes. Okay. So stirring approximation, it's a very nice one. It says something about how the factorials, or mainly how the logarithms of factorials, are behaving when the argument of the factorial is very big. Because basically, if I have n factorial, it equals to a gamma function of n minus 1. And what is a gamma function of? Gamma function of x. This is a gamma function, which is a special function that you've probably already seen somewhere somehow is a multiplication, is an integral from 0 to infinity of x. I'm sorry, it's a function of n. X to the n minus 1 e to the minus x dx. And I compute, and I can approximate. And I can approximate by using methods called Stita's descent. I don't think I should. I don't think that you've seen it because it's already graduate math class level. But for our purposes, actually, Stirling approximation is taking n factorial, representing this as a gamma function, and calculating or approximating this integral, which is called a gamma function, and giving us that the logarithmic of n factorial goes like n log n minus n. This is the Stirling approximation. So what we are going to do next lesson, we're going to take this formula, plug it into this representation of the entropy, okay, and actually obtaining a very much more nicer representation of the entropy. We're continuing from where we have started, finished. So we have the we are going to use the Stirling approximation in order to describe in a more, I'll call it normal way, this behavior of the entropy. Okay, so let's see what we have there. So S equals to K Boltzmann, and instead of log of u divided by h bar omega 0 plus 3n minus 1, what we have over there is K Boltzmann, u divided by h bar omega 0 plus 3n minus 1 multiplied by ln of u divided by h bar omega 0 plus 3n minus 1. I will erase this part of the board because I'm going to need it. Minus u divided by h bar omega 0 plus 3n hat minus 1. I close the parenthesis. And we have K Boltzmann. Now we are developing the logarithm, this logarithm and this logarithm. So minus K Boltzmann of 3n minus 1 multiplied by ln of 3n minus 1 minus 3n minus 1. Close the parenthesis. And I have an additional term, which is this guy. So I have minus K Boltzmann of u divided by h bar omega 0 multiplied by ln of u divided by h bar omega 0 minus u divided by h bar omega 0. Great. So this is it. But it's still really, really ugly. And so what should we do next? First of all, we're talking about big system. We have huge number of oscillators over there. So this minus 1, it doesn't really matter. Okay? We can neglect it. So each time we have minus 1, we will just erase it everywhere. Okay? Second of all, well, let's try and open this, only this part over here. Okay? Because we see that some terms are very similar to what appears in the two lines below. We have UH bar omega 0, we have UH bar omega 0 multiplied by some ln, minus UH bar omega 0, and we have here minus UH bar omega 0. So for example, we already can see that this minus UH bar omega 0 and this plus u h bar omega 0, we can erase, okay? And we also can perform exactly the same thing for the 3n bar. So we have here minus plus 3n bar. Here we have minus minus, which is a plus 3n bar. So this guy disappears. And the only thing that we left with is this term, this term, and this term. So only the logarithms. And the logarithms are also look somewhat similar, right? It's u divided by h bar multiplied by some ln. Here, u divided by h bar omega 0 multiplied by some ln. So what we are going to do is we are going to make two separations for this log. So we write, first of all, we write that we have u divided by h bar omega 0 multiplied by ln u divided by h bar omega 0 plus 3n hat. This guy equals to u divided by h bar omega 0 multiplied by ln of u divided by h bar omega 0. Here we have 1 plus 3n hat divided by u divided by h bar omega 0. Okay? So I just taking the common multiplier u divided by h bar omega 0 from those two parts. Okay? And this equals to u divided by h bar omega 0 multiplied by ln of u divided by h bar omega 0 plus u divided by h bar omega 0 of a ln of 1 plus 3n u divided by h bar omega 0. Okay? And when we look now, so we have taken this multiplied by the ln. Okay? And we left with two terms. But this term is a plus. And here we have the same term with a minus. So you see here u divided by h bar omega 0 ln u divided by h bar omega 0. Okay, so we can erase this term and this term too. Now we can go and say, well, we also can perform the same trick when we have 3n bar multiplied by logarithm of u divided by h bar omega 0 plus 3n bar. This we will do on this part of the board. Little by little, just eliminating all the terms in this equation. So let's see what happens if we have 3n ln of u divided by h bar omega 0 plus 3n bar. Take both through 3n ln of, now as a common multiplier we take out 3n bar. So ln of 3n bar multiplied by 1 plus u divided by h bar omega 0 3n bar equals to 3n bar multiplied by ln of 3n bar plus 3n bar multiplied by ln of 1 plus u divided h bar omega 0 3n bar. This term, 3n bar ln 3n bar, is exactly this term over here. Okay, so we will erase them. Eventually what we left with is this term, 3n bar ln of 1 plus h bar omega 0 3n bar, and this term, u divided by h bar omega 0 ln of 1 plus 3n bar u divided by h bar omega 0. Okay, and we'll just write this down as the final result for the entropy, which is much more nicer than this result over here. So what we eventually have, so we have S equals, so this term, 3n bar ln of 1 plus u divided by 3n bar h bar omega 0 plus this term over here, u divided by h bar omega 0, u divided by h bar omega 0 multiplied by ln of 1 plus, and here I have 3n bar h bar omega 0 divided by u. This, I should say this S K Boltzmann, and K Boltzmann here. And this is my entropy in the limit when the n large and u large. Out of this quantity, I can obtain a thermodynamical equation that will involve temperature. I don't have volume over here. Okay, I have number of particles, but I don't have volume over here. But temperature, I can have, because I remember what temperature is. Temperature is 1 over T equals ds du. U is my energy, S my entropy. I know how S depends on U. I've forgotten about the number of states. I've used U in order to describe what is my number of states, how my number of states is behaving. And now I have left only with thermodynamical properties. Okay. So let's see, out of this equation, can we solve it? Take the derivative of S. We will obtain a function. The derivative of S with respect to U is a function that will depend on n bar, U, h bar, omega 0. And then we can relate the energy of the system and the temperature of the system. Okay? After writing this thermodynamical equation. And if we know the energy of the system, we can actually calculate what is the average energy of each oscillator. Or even going forward, we can compute what is the specific heat of the system. Okay? We can compute CV or CX or whatever. Right? Because then it will just be CV will equal du dt. The volume is constant. Okay? So everything that we want to know about the system in terms of thermodynamics is going to be easily obtained the moment we find what is the energy, or how the energy depends on the temperature. And we are going to obtain this by using this equation over here, the definition of the temperature. Okay, so let's see how we are going to perform this. So we take this equation and we perform a derivative. So it's ds du. It's 3n k Boltzmann multiplied by 1 divided by 1 plus u divided by 3n h bar omega 0. Alright, multiplied by 1 divided by 3n bar h bar omega 0, okay, plus 1 divided by h bar omega 0 multiplied by k Boltzmann of ln of 1 plus 3n h bar omega 0 divided by u. Okay, and we also have K Boltzmann. I'm sorry, K Boltzmann. You know what we have here? K Boltzmann U divided by h bar omega 0. Okay, multiplied by their derivative, so 1 over 1 plus 3n h bar omega 0 divided by u, okay, multiplied by what? Multiplied by 3n h bar omega 0 divided by u squared multiplied by minus 1. We take here everything into account, simplify, it's really pretty simple, and we obtain a final relation which tells us that 1 over t is equals to k Boltzmann divided by h bar omega 0 ln of 1 plus 3m bar h bar omega 0 divided by u, okay? Or we take an exponent, or let's rewrite it and we say that h bar omega 0 divided by k Boltzmann t equals to ln of 1 plus 3n h bar omega 0 divided by u. We take an exponent of both parts, right? And what we get is that exponent of h bar omega 0 divided by k Boltzmann t equals to e of a logarithm is just simply what stands here is 1 plus 3n bar h bar omega 0 divided by u. So we work our way into where we basically want to obtain u as a function of t and all the other parameters. So we now can actually take u out of this equation, right? We're left with u divide u. Okay, so let's write it down slowly. E to the power of h bar omega 0 divided by k Boltzmann t minus 1 equals 3n bar h bar omega 0 divided by u. We obtain that the energy of the Einstein model for the whole system is simply 3n bar h bar omega 0 divided by e h bar omega 0 k Boltzmann t minus 1. This is the energy of the system. Okay? What can we get? We can get, for example, what is the average energy per atom, per oscillator. We obtain that u divided by 3n is the energy per oscillator because we have n atoms. Each atom has 3 degrees of freedom. We obtain it simply 1 over e h bar omega 0 divided by k Boltzmann t minus 1. We can continue now on and obtain the specific heat of the system. Okay. There actually not need to because we will compute it for another model. But what we have seen here that we started from microscopical model. We use our constraints. We work a little bit of mathematics using a Stirling approximation, and we obtain a pretty simple equation for the energy. We can use this energy basically is the state function of the system. We can use the state function to define whatever we like to compute all the other quantities that we are already observing in thermodynamics, and etc., etc., etc. It's pretty simple, right? The only thing that matters here is your starting point. Your starting points and your constraint. What is your basic model, and what ensemble are you using? You're using microcanonical ensemble or something else. Afterwards, this is just some mathematical technique, combinatorial technique. We will see that actually we can do it a slightly different way. And after you just rotate this crank and you apply all of this apparatus, eventually obtain a state function. What you do with the state function is something else, but you can use the state function in order to compute quantities that can be observed from the experiment under assumption that ergodicity works here. And here you go, you have predictions. And if your predictions work well, then your microscopical model is actually, maybe it's worth defining it on describing the system in those terms. If it shows you something completely different, then you know, well, my microscopy is untrustable. Okay? But this is how you can actually go and say, well, what happens on the microscopical level? This is what happened. This is what's important. How you prove it? You obtain a general observable, and you say, well, do I see it actually happens in nature? Yes or no? And we go from here to our next example, which is a two-state model. It's even simpler than the Einstein model. So what is a two-state model? Two-state model says, well, I have a general system which is composed of a lot of particles. Each particle can only have two systems, two states. Okay, so this is why it's called a two-state model. Two-state model. So I have a lot of particles. Each particle have two energies. Zero energy and an epsilon energy. Okay? So each particle can be either here or either there, and can jump between those two energies. This is even simpler than the oscillator picture that we had before. In the oscillator picture, we had many quantas of energies. In this guy, well, there are only two. Okay? But I have a lot of them. So this is for each particle. Total number of particles. Number of particles is n bar. So I have a huge number of particles, each of which can choose one specific energy, okay? And we go from here. I can ask myself, and the total, what I also assume, U is the total energy is constant. In order to provide a function of state, what I need to do, I need to compute all different states, and I know that all the different states are unequal, okay? And I can go from there. So again, like in the Einstein model, what I need to do now, I'm actually need to count the different number of states. Again, combinatorial question. So what we have here, we have the total number of particles n bar. The total energy is U. Now I can ask myself, out of n bar particles, how many are in a state that have epsilon as energy? How many out there? So it's simply U divided by epsilon. It's the number of particles that have epsilon as energy. Why is that? We take this number, this is the number of particles that have epsilon as energy, we multiply it, each of them have epsilon energy, U divided by epsilon multiplied by epsilon is simply U. Okay, this is our constraint. The total energy of the system is U. What is the energy 0, or how many particles have energy 0? It's simple. N is the total number of particles. U divided by epsilon is the particles that are occupying the state with epsilon as energy. So everyone else is at 0 energy. So n is the total number. U divided by epsilon is the number of particles. Is the number of particles that have energy epsilon. So n bar minus U divided by epsilon is number of particles with energy 0. You may ask yourself, well, what is the physics here? Right? What are the particles that only have 2 states and can never be excited to higher states? So what I'm assuming here is there are maybe some states up way above, but the gap between this state, and all the states that lie above it is very high. Very large, I'm sorry. It's very large. And basically, the temperature or the conditions of the systems are such that the particle, no particle, ever is capable of actually going over this gap between epsilon and the next level. Okay? This is our assumption. So all the states, all the different configurations that can be in the system, 3 particles with epsilon, 4 particles with 0, etc., etc., must satisfy what? That U divided by epsilon are the number of particles that have epsilon, n minus U divided by epsilon is the total number of the particles that have energy 0, and all the states are exactly equal. So what is this number, the number of different states that we have in the system, U, is basically take n bar particles, which is they can have different states, and choose out of those states U divided by epsilon that will have energy epsilon, and choose n bar minus U divided by epsilon particles that will have 0 energy. What is the number of states? Is just n bar factorial divided by what? Divided by the number of permutations of U epsilon, U divided by epsilon factorial, and n bar U divided by epsilon factorial. This is always the formula. If I have n apples and I want to divide them or choose U divided by epsilon apples, it's just n apples factorials divided by the number of apples that I choose and all the other perturbations for shufflings. Okay? So this is the total number of states. The total number of states. I see now that it's only dependent on what? On the total number of particles, the energy per particle, okay, or the energy level that each particle can occupy, and the total energy U. What I'm going to do now, exactly what I have done before, I will write as S of K Boltzmann ln of omega, which will simply K Boltzmann ln of n hat factorial divided by U divided by epsilon factorial, and n bar minus U divided by epsilon factorial. Okay? I'm going to use Stirling approximation in order to write this logarithm, and afterwards I will obtain entropy as a function of energy. Later on, I will take my thermodynamic equation, which relates the temperature to the derivative of the entropy with respect to the energy, and I will obtain a relation that has energy and entropy and temperature inside of it. Okay, so again, a function of state, a macroscopical function of state. But first, some math. So the math is here for these problems always involves Stirling approximation and afterwards taking derivatives of those guys. All right. So what we are going to do, first of all, starting, right? So we have S equals K Boltzmann, ln of n bar factorial minus K Boltzmann, ln of U divided by epsilon factorial, minus K Boltzmann, ln of n bar minus U divided by epsilon factorial. Right? We're using staring. The staring tells us that it's simply K Boltzmann n bar ln n factorial minus n minus K Boltzmann U divided by epsilon ln U divided by epsilon minus U divided by epsilon minus K Boltzmann of n bar minus U divided by epsilon multiplied by ln of n bar minus U divided by epsilon minus n bar minus U divided by epsilon. Okay. After we got this nasty expression, well, we look what we can already throw away, and what we can throw away is n ln, so here we have minus n, and here we have plus n. So this guy eliminates this guy. Also we have minus u divided by epsilon, and here we have minus minus. So no, here we have plus u divided by epsilon, it's minus minus, and here we have minus minus minus, so it's minus u divided by epsilon. So we eliminate this guy. Okay. Afterwards, what we do? Exactly the same thing that we have done previously. So we have here logarithm of n factorial minus u divided by epsilon. We can take out. We can take out this, or either n bar out, and then we'll have n multiplied by logarithm of n factorial, and then this guy will eliminate. Or we can take logarithm of u divided by epsilon. I can go a little bit slowly over this procedure. So what we have here, I'm only looking on this part over here. Okay, so this part is n bar divided by u divided by epsilon of ln of n bar minus u divided by epsilon. Okay, and this equals to n factorial ln n bar minus u divided by epsilon minus u divided by epsilon ln of n bar minus u divided by epsilon. Okay, and this equals n bar ln n plus n bar ln of 1 minus u divided by n epsilon minus u divided by epsilon ln of u divided by epsilon minus u divided by epsilon ln of n bar divided by u divided by epsilon minus 1. Okay. So this is this. And we have to compare it with what left, with n ln n. And you already can basically throw this guy and this guy away. What else we have? U divided by epsilon ln epsilon. This guy goes together with this guy. Okay. So basically we eliminated everything except this part and this part. So let's write this down. So what we have left with is S equals to K Boltzmann n factorial ln of 1 minus u divided by n bar epsilon minus u divided by epsilon of ln of n bar divided by multiplied by epsilon divided by u minus 1. All right. Nice, right? Almost nice. Okay. So this is the relation between the entropy and energy. We want to obtain a relation that gives us energy. Entropy we cannot measure, but energy and derivatives of the energy and temperature. So 1 over T is simply ds du. We do this, what we obtain, that 1 over temperature is simply K Boltzmann divided by epsilon ln of n bar epsilon divided by u minus 1. Okay. Now that we have this relation, we work backwards. We now solve it in order to obtain what is u as a function of the temperature. So how we go from this? We go that K Boltzmann, epsilon divided by K Boltzmann T equals to ln of n bar epsilon divided by u minus 1, exponentialize both parts, okay, and obtain that an exponent of epsilon K Boltzmann T equals to n bar epsilon u minus 1, and then we obtain that u equals to n bar epsilon divided by e to the power of epsilon divided by K Boltzmann T plus 1. Great. So the energy goes in a very specific way, but actually what is very informative from this behavior is what? Is the specific heat. So let's go and obtain the specific heat that in our case would be du dt. Usually it's what? Tds dt. But Tds is what? Is du. So the specific heat is du dt in our case. What we do, we take this guy over here, okay, and we take the derivative with respect to what? With respect to this, to the temperature, gives us n bar epsilon multiplied by 1 over e to the power of epsilon divided by K Boltzmann T plus 1. All of this multiplied by minus 1. Multiplied by what? By e to the power of epsilon divided by K Boltzmann T. Okay? Multiplied by epsilon divided by K Boltzmann T squared multiplied by minus 1. Am I right over here? It seems right. Okay, so eventually minus 1 and minus 1 cancels out. We have this guy. 1 over here. It seems kind of right. This is to the power of 2. This is to the second power. Okay, if we plot this, and this is why it's informative, we plot our C as a function of k Boltzmann T divided by epsilon. We obtain a nice feature. This feature is that it starts from 0. It starts from 0 and it grows. What we usually think about specific heat. The specific heat is how much the energy of the system, or the entropy. The energy of the system changes as we change the temperature. So we increase the temperature, the energy of the system increases. We increase it a little bit, the energy of the system increases. But at some point, so it will always should go up. Maybe eventually it should saturate. All right. So this is our expectation from the specific heat. Okay? It should go up and up and up and up. Maybe saturate. What happens to this guy over here? That it indeed goes up. But at some point, well, we see that for t large enough, because of this 1 over t squared, or 1 over t, we have that it actually does not saturate and not grows, but it falls down and approximately goes to 0. This is quite interesting. Where this behavior is coming from? Okay? Because it's not intuitive. Intuitively, we would expect that the specific heat will grow higher and higher and higher. Or maybe it eventually will saturate, but it definitely won't fall to 0. Okay? Specifically, this maxima over here, it's called a Schottky pump, or also Schottky anomaly. Why it's anomaly? Because we do not expect a maxima for the specific heat. Okay? We expect it to be a monotonic function. So what happens? Remember, we have 2 energies. We have only 2 energies. So the particles are either sitting here or sitting there. So for low enough temperatures, all the particles should sit in the ground energy. As we increase the temperature, more and more particles can actually go above this gap of epsilon and occupy the next possible level with energy of epsilon. So if we increase the temperature, more and more particles are going upwards. We increase the temperature and the energy of the system increases. We increase the temperature again and again and again and again. And then it still continues to grow. But at some point, as we continue to pump up energy or pump up the temperature, what will happen, more and more particles will occupy the second level, and they do not have the freedom to go upwards. So this temperature is not high enough in order for them to overcome the next gap. They will be all concentrated somewhere here, a lot of them. So the energy of the system is not changing as we increase the temperature. It's actually, so the derivative must fall down towards 0. Right? And this is exactly what we see over here. So this anomaly, this maxima, is basically representation of the fact that we have 2 states in the system, marginally speaking, 2 states of the system, and that the system cannot or still cannot penetrate to the higher level systems, and only those 2 states completely defining the whole dynamics or the whole behavior, statistical behavior of the system. This quantity we can measure macroscopically. Okay, we look on the system, on some specific system. We can measure the specific heat. We change how the energy of the system is changing as the global energy of the system is changing as a function of the temperature. We see this anomaly. We can say, well, actually, we now can understand a little bit of what's going on inside. Okay? We can assume that there are two energies of the system, and in this range of the temperatures, there are two generally accessible states, and that's it. Okay? So it's a nice prediction by using macroscopical quantity and connecting it with the microscopical behavior. Okay. I'm going to my third example for today, which is a polymer model. A polymer model. You'll have to excuse me. I'm going to bring my demonstration of the polymer. Just a second. Okay, so this is a simple example of what polymer looks like. It's a long molecule, it's crumpled, and somehow it has a very strong interactions between different parts on short time scale, on short length scale. Okay, on longer time scales they tend to forget about each other. The interactions between different monomers is actually very complicated. And we can do a lot of experiments with this. And also a lot of materials are based on the properties of long molecules. Now, specifically, for example, what now you can do, you can perform pooling experiments with the models, with those polymers, in a physical lab. So you'll have your polymer, you will attach one end to a wall, you let it freely do something in space, okay? And then you pull it with some specific force. Okay, so it's somehow crumpled, I don't know, and you try to pull. And as you pull, you measure the force. And you pull, nothing happens, and then, you will see a jump. Why? Because it's released from some specific knot that was actually constructed over here. And you can do, and you can learn a lot of the properties of the polymer by performing those pooling events. Okay. Another types of experiments, so for example, the lab in Ilan is actually performing those experiments. The lab of Yuval Gurini in the nanocenter. So for example, you can attach your polymer to a floor. It will do something in space. Okay. And then you can look on the bead that is usually golden bead, but we'll plot it in blue. It is attached to the other end of your polymer, right? And this bead is performing some sort of a motion, okay? And this motion is described by some effective force that this polymer is actually applies to the bead, and you can study those forces by looking as a function of time on the different positions of this bead. Now this polymer is constructed from small different monomers. Okay, if you will look closely on it, so it's constructed from small molecules which are pretty solid. So on a small scale, you can always plot your your polymer as constructed of a lot of different monomers. But generally speaking, your polymer is effectively just some sort of a spring, okay? Like a spring, in classical mechanics. So it's a spring. It has a spring constant. You can actually see this from experiments on specific length scales. Although it's very complicated structure, it's composed of a lot of smaller molecules that have some specific bending to it, that it has elastic properties. But you can look on this as a spring. But this spring has one specific, very interesting property. So if you have a spring, like this is your spring, and you just pull it, and as you pull it, you can compute the spring constant, right? So the spring constant is actually how hard the spring tries to resist to an implied force. Okay, so and usually it's something, it's just called a spring constant. So for regular materials, okay, metallic materials for spring, the spring constant changes as a function of temperature. Okay, so I heat my spring up a little bit, the spring constant will change. The hotter the material is for regular springs, the hotter the material is for regular springs, the spring constant goes lower, okay? So for temperature 1, I have one spring. For a much more higher temperature, the spring constant would be much more lower, and it's easier to pull spring apart for higher temperatures, right? It's a nice properties of the metals and their elastic properties. But look on this polymer, okay? So this is a long molecule, and this is somehow crumbled alongside, I don't know, something. Okay? What is the increasing the temperature does to this long molecule? Okay? It does something like this. Okay? And it crumbles along, and I actually allow it to perform very large fluctuations. At some point I look on this in very high temperature, it crumpled already, okay? And I try to pull it apart. It's much more harder to pull it apart now as compared to the situation where it was completely free. It's hard actually to untie this right now. This is what happens to polymers, real polymers. Wow. Okay? So it's easy to pull it apart, and when it's crumpled, okay, let's do this again. No, I have to touch the end. Okay. And when it's crumpled, it's harder because of those guys, or those specific loops. Okay? Now, can I actually quantify those forces? So those forces are not properties of the material, right? Those properties are properties of the temperature of the system. For a regular spring, where I do not allow those large conformational space, and I'm looking on the material itself, the spring constant will drop down as I increase the temperature. But for a long molecule, as a polymer, when I allow this big fluctuation, and this is what temperature is, I'm allowing much more states to be occupied, okay? What I see in experiment is that now is harder to pull it apart. Well, now it's free. But let's assume that I managed to do this again. Okay, now it's much more harder. Okay, so let's see if we can come up with a simple model for the polymer that will enable us to actually see this effect in nature. Because it's not the properties of the force, the metallic properties, or the properties of the strength between different monomers. Okay? Is the properties that we allow much more states for the system, and because of this additional states, when we try to pull the system apart, the system is reflecting in a sense that it's much more harder to pull it apart right now. Okay? So this is not real forces as we know it. Those are entropic forces, because for the different small monomers, the forces between them are now lower when we increase the temperature. But the general huge system, which composed from a large number of monomers, something different happens because we allow for more states. When we heat the system, we allow it to occupy much more states. And now there are additional forces. Those forces are not regular forces that we can write from this, from the interactions. Those forces are coming from the states, additional states that are entropic forces. So let's see, can we come up with a very simple model in order to quantify this effect? Or at least look at it in a qualitative fashion. So in physics, in statistical physics and statistical mechanics, if you try to build a very realistic model of a polymer, okay, we will get nowhere. If I'll try to include all different forces that are actually acting on different monomers and how this monomer is interacting with this monomer, I will include all the quantum mechanics and all the chemistry, which is very, very complicated, inside my model. I will have something gigantic, but something that I can never solve. The purpose of statistical mechanics is, let's try some parts of the reality and use only them. It will provide us very general results, but nothing specific about this specific polymer. In order to understand something very specific about molecular properties, I need to do quantum mechanical calculations, I need to do simulations. In order to understand qualitatively what's happening to a big molecule, okay, I need to include very little in my model in order to actually eventually solve it. So my model goes as follows. I have a wall, and I have a polymer which are consisted which is actually built from small monomers, and each monomer can be either in the x direction or either in the y direction. Okay, so my polymer is actually, it looks like this. Right? So there's a lot of monomers. Each monomer can have 4 different states. This with the direction of x, perpendicular to the direction of x, negative x, negative y. Okay? And all of them have exactly the same length. So we have something pretty big. At some point, I just connect it to a pulley and pull it down with some tension tau y. Okay. This distance is Ly, and this distance is Lx. Okay, so this is the assumption of how the monomer is constructed. I have the total number of n bar monomers, n bar, the total number of monomers. So each segment here is a monomer, and I have n bar of them. Okay. Now, in order to statistically describe this guy, I should say something about the energies. The energies of each monomer. Okay. So what am I assuming? I'm assuming, because I'm pulling this big long molecule in the x direction, I'm assuming that the monomers prefer to lie in the x direction and that pay some energy in order to be in the y direction. Okay? Because I'm pulling them apart, there is a preferable energy and there is an energy that the system will take, but it has to pay something in order to be in this configuration. along the y-axis. So what I'm saying is that if the monomer in the direction of x or negative x, its energy is 0. Energy of a monomer. So it's either 0 in x direction, or it's epsilon, I write it down as epsilon, yes, or it's epsilon if it's in y direction. So now I have energy per monomer. I can look on its configuration. So this monomer, its energy is 0. This monomer, its energy is epsilon. This monomer, this energy is 0, and this monomer, its energy is epsilon. So this is epsilon, this is 0, this is epsilon, this is 0. Okay. I can ask myself, what are nx plus, what are nx minus, what are ny plus, and what are ny minus? Nx plus is the number of monomers that are along x plus direction. This is the number of monomers that are along the negative x direction. Ny plus, number of monomers along positive y, and ny minus, number of monomers along negative y. Now, I'm going to use those guys, nx plus, nx minus, ny plus, ny minus, in order to describe the number of states. Because for each monomer, okay, what I can do is, well, I have total number of n bar monomers. Now, I have somehow, in order to construct a specific state of the system, what I need to do is I need to choose from n bar monomers, nx plus monomers that will go up, nx minus monomers that will go not up, nx plus to the left, nx minus to the right, ny plus up, ny minus down. All different configurations are such that I chose from n bar, nx plus, nx minus, ny plus, ny minus, but I need to satisfy the constraints. What are the constraints? The constraints are that the length of the molecule in the x direction is Lx, and the size of the end-to-end distance in the y direction is Ly. Those are my constraints, and the total number of the monomers in Sn bar is additional constraint, and the total number and the total energy is U is also additional constraint. So let's write our constraints here. Constraints. N bar, total number of monomers. Lx, end to end distance in x direction. Ly, end to end distance in y direction. And also I have that U is the total energy. So I need, in order to describe thermodynamically this system, what I need to do is to write the number of the states, which is by choosing n from n bar, nx plus, nx minus, ny plus, ny minus, such that all of these constraints are satisfied. So n bar is constant, nx plus, nx minus, ny plus, ny minus must be written in form of n bar, lx, ly, and u. So what we have here is that nx plus nx minus plus ny plus ny minus equals n. We also have that nx plus minus nx minus equals lx. This is the number of steps that I perform to the right minus the number of steps that I perform to the left is the end-to-end distance. This is Lx. The same goes for ny plus minus ny minus equals Ly. The end-to-end distance in the y direction is the number of steps that I perform to the up minus the number of steps that I perform down. This is the third constraint. The fourth constraint, the total energy. So we know what is the total energy. The total energy is the number of steps that are either in the y, that are parallel to the y-axis, which is ny plus ny plus ny minus equals u. Okay, we solve this, and we obtain that nx plus equals 1/2 n bar minus u plus lx. Nx minus equals 1/2 n bar minus u minus lx. Ny plus equals 1/2 u plus ly. And ny minus equals 1/2 u minus ly. So now that I have nx represented in a constants that are n bar u lx, nx minus again represented in a constant terms of n bar u and lx, the same for ny plus, the same goes for ny minus. I can write the total number of states as, which is basically n bar divided by nx minus factorial, nx plus factorial, ny plus factorial, nx minus factorial, and ny minus factorial. But I cannot just use this form. I need to use nx plus, nx minus, ny plus, ny minus in terms of the constants. So omega is simply n bar divided by 1/2 n bar minus u plus lx factorial multiplied by 1/2 n bar minus u minus lx factorial multiplied by 1/2 u plus ly factorial multiplied by 1/2 u minus ly factorial. Nasty form. Really nasty form. S is k Boltzmann ln omega. What we have to do next? we actually don't really have time to do anything next, but I'm just going to write down the final equations and I will publish the full solution. I take the entropy definition, I apply Stirling, and I obtain something. Then I exponentialize everything, etc., and I obtain the relation 1 over t is equals ds du. Eventually, I can obtain equation that relates energy to temperature, and I can also obtain equation that relates tau, the force that I'm pulling with, also to S. Why? Because I know that dou S dou L y equals minus tau y divided by Ly. I don't have time exactly to explain by how the entropy changes, or the energy is zero, and the energy is composed from changes in entropy and changes in the energy and the tension. Eventually, I can obtain everything. I can work out with those equations. I can relate the temperature to the energy. I can relate the energy to the tension in the spring. Okay? I work everything out, and what I eventually will obtain, and I will publish this online in the Moodle, what eventually I will obtain is that Lx equals tau x n bar divided by k Boltzmann t multiplied by 1 over plus 1 minus epsilon k Boltzmann t. And dou Lx dou tau x, which is how it's hard to increase the length of the polymer by changing the force. This is exactly the spring constant. Okay? It will equals to n bar divided by k Boltzmann t multiplied by 1 plus e to the minus epsilon divided by k Boltzmann t to the power of minus 1. We see that it decreases as I increase my temperature. I'm sorry, it's actually, it increases, I increase my temperature. That's coming from this term. What I'm trying to say, and I really don't have time, is that if I would attempt and see what happens to the interactions between the different monomers, I wouldn't see anything. And actually only inclusions of different states, accessible states, which came from this definition over here, and the definition of the total number of states, and actually using the entropy, and only entropy over here. I didn't have any interactions whatsoever between different monomers. But I still obtained this effect that it's much more harder to pull as the temperature goes up. Why it's like this? It's only because now I have much more states. And this exponentialization of the number of states as I increase the temperature, as I increase my energy, this is what brings me down to this situation that it becomes harder and harder to pull the system apart. Okay. That's it, and I will publish today or tomorrow the whole solution with all the details and how actually I arrived to this equation over here. It's a little bit longer. Thank you.